Bonjour, bienvenue, and welcome everyone to Perimeter Institute's public lecture series. My name is Emily Petroff, and I'm Perimeter's Associate Director for Strategic Partnerships, Grants, and Awards. I'm delighted to welcome you back to the Mike Lazaridis Theater of Ideas here at the Perimeter Institute in Waterloo. C'est un grand plaisir de vous accueillir ce soir à l'Institut Périmètre pour ce qui, nous sommes sûrs, sera une présentation fascinante. Perimeter Institute was created to be a gathering place where people can come together like we're doing tonight to ask the big questions about the universe and search for the big answers. Perimeter will soon celebrate 25 years of bringing people together from all paths, researchers, students, the general public, teachers, to explore the fascinating world of physics. But people on this land have been asking the big questions about the universe for thousands of years. Looking up at the night sky and understanding our place in the cosmos is a human constant throughout the ages. We acknowledge that Perimeter Institute is situated on the traditional territory of the Anishinaabe, Haudenosaunee, and Neutral peoples, and is located on the Haldeman Tract, the tract granted by the British to the Six Nations of the Grand River and the Mississaugas of the Credit First Nation. Nous saluons et remercions les divers peuples qui nous ont précédés et nous nous engageons à agir de manière responsable et collaborative pour faire avancer la quête de savoir pour le bien de tous. Et nous remercions les Anishinaabe, les Haudenosaunee et les Neutres pour leur accueil. For those watching the live webcast, please join the conversation online. We are at Perimeter on Twitter or X. And if you have a question for our speaker, you can ask it with the hashtag PILive. This week, Perimeter Institute has been hosting a fascinating workshop called Dark Matter First Light, which brings together experts to discuss the ways that dark matter impacts the formation and evolution of stars and galaxies. This workshop, which concluded today, focused on the new observational programs and techniques coming online and new modeling tools that may enable a better understanding of the mysterious matter you'll hear more about tonight. And now, it is my great pleasure to introduce one of those workshop attendees and our speaker for tonight. Theoretical physicist Flip Tanedo is an associate professor at the University of California Riverside, and his research seeks to determine the fundamental physics of dark matter. He's a 2021 Career Award winner from the U.S. National Science Foundation and a 2020 Hellman Fellow. He has appeared in popular media on shows like Nova and Science Friday. Dr. Tanedo grew up in Los Angeles and is a proud product of the Los Angeles Unified School District. He earned his bachelor's degree in physics and mathematics from Stanford University before completing graduate studies at Cambridge University, Durham University, and Cornell. He spent 3 years as a Chancellor's Advanced Postdoctoral Fellow at the University of California, Irvine, before moving to Riverside. Dr. Tanedo is the first Filipino-American professor of physics, and he has served in several official capacities as an advocate for equity in academia. His research focuses on developing a fundamental theory of dark matter. His work has interesting intersections with fields including particle cosmology, machine learning, and information. Tonight, he will discuss recent developments in the search for dark matter and how the scientific community can come together to find new answers. Please join me in welcoming to the stage Professor Flip Tanedo.
Good evening, everybody. My name is Flip. I am a theoretical physicist, and I work on dark matter. So, quick show of hands, how many people have heard of dark matter? Good. How many people here know what dark matter is? Now, one hand up. So, we're all in good company. We are all in the same tribe. Very good. We're all in the same boat. All right, so let's get started. Here is my very best attempt at a completely realistic picture of dark matter. It's completely invisible. Okay, so that's not very interesting. If you'll permit me a little bit of artistic license. Here is astronomers love to false color their photos. Here is a false color illustration of dark matter. And I've even done the extra work of sketching where we are. This is the Milky Way. and we were sitting in this bubble of dark matter, this big blue bubble of dark matter. And if we were to zoom out, again in this artistic rendition, we would notice that our bubble of dark matter is actually sitting in a cluster of bubbles of dark matter. And I didn't draw it here, but if you looked into each of these bubbles, most of them also happen to have galaxies sitting there. That's interesting. And David Foster Wallace had a story once where there were two fish who meet in the ocean. And the first fish says, "Isn't it great that we have water?" And the second fish says, "What the hell is water?" And this is where we are as a scientific community thinking about dark matter. What we know is that we are little fish living in oceans of dark matter. There are bubbles in a cluster of other bubbles of dark matter. And there is so much that we do not know, but we know that that much is true. And this is our cosmic mystery. So like all mysteries, there's a who, what, when, where, why, and how. And we won't quite go through them in this order. This is a piece of art. It's an installation at the Los Angeles County Museum of Art. And in this dark matter business, we have a phrase that we overuse. And the phrase is looking under lampposts. Looking in the dark under lampposts, looking for truth, finding some angle to learn about this mysterious thing that we're in. So this is going to be our guidepost. These are my attempts at lamppost for understanding not just what is the puzzle, but how is it that me, a theoretical physicist, which you might already think, and my colleagues do think, what can you possibly do if you don't have a lab, am tasked with understanding a substance that surrounds us that we can neither see, nor touch, nor smell, nor taste, nor anything else, to the best of our knowledge, and then somehow do science on this. It's a bit of a tall order, isn't it? So let's start with what. And in fact, what I need from you today is to start with the assumption that dark matter exists. And there's one thing that we know pretty well, which is roughly how much there is, right? Of all this matter, all the stuff in the universe, all the things you would call chunky matter-like things, we are about 15%, and most of the rest of it is dark matter. Are we okay with that? We're all on board? Anybody skeptical? Any physics students in the room? Any science students in the room? Very good. And I will speak for you. You are all feeling very uncomfortable right now. You do not like someone sitting here telling you there's this invisible thing that surrounds the universe and it's real. I just need you to believe me. All right, so let's not just take this completely on faith. There is evidence for the existence of something more, something that we do not understand, for these bubbles of dark matter that we live in. And the evidence comes from the sky. When we look at the motion of stars in galaxies, when we look at motions of clusters of galaxies that happen to be pancaking towards each other in the distant sky. And when we look at the photons from the cosmic microwave backgrounds, the very first photons from 13 billion years ago reaching our telescopes today, each of these probes give indelible evidence that there is stuff that is clumped up that cannot be explained by protons, neutrons, and electrons and their cousins. Everybody convinced now? Are we all on board? Physics students are all on board? Okay, so one of the organizers for the conference that I've just come from is Katie Mack, who is sitting here in the audience. She's a faculty member here at PI. You've heard of her? And I had the special joy of attending one of Katie's colloquia at the Aspen Center for Physics a few years ago. And Katie gave us a fantastic talk, which I am summarizing in this board, which you cannot read, deliberately so, because I don't want to give that talk. I am not qualified to give that talk. But here are 12 pieces of evidence that Katie has organized for why we are so sure that dark matter exists. Now, you might be able to read the titles. What is important here is that there are many reasons. What is important here is that they're complementary. And so it's not just that you see a few stars. It's not just you see a galaxy cluster. It's not just that you observe this cosmic microwave background. That's like saying if it walks like a duck and talks like a duck, it's probably a duck and therefore dark matter. What all of these different pieces of evidence are telling you, taken at different length scales, at different times in the cosmic history, is not only that it walks like a duck, it talks like a duck, it's got feathers, a beak, it has duck DNA, and it tastes great with hoisin sauce. So that doesn't mean that it is definitely dark matter. Like this guy on stage is saying it's dark matter. But what that does mean is if it is not dark matter, something really strange is going on. The most conservative thing we can say is that all of these different pieces of evidence are pointing to something that looks like stuff, matter, that is not the stuff that we are used to. So that's where we are. It would be amazing if it weren't dark matter. Something way more exciting is happening. So the other thing that you might notice, all of this evidence is coming from the sky, astronomy and cosmology. There is no problem with inferring that dark matter exists from astronomy and cosmology. I am a theoretical particle physicist. The problem is in my tribe. The problem is, what is this dark matter? So let me jump to a very different type of question. When is dark matter? When? Why is it that we're studying dark matter now? And this is where the apology of my talk comes in. So let me give you a very biased, it's almost true. Anybody here who's a specialist will know this is not quite true, but this is morally true. History of dark matter. And this is a history of two tribes. Particle physics, where the problem is, and astronomy, where the observations are. And this goes all the way back, at least until Orton Zwicky, this is Fritz Zwicky, who observed in their early telescopes that the motion of galaxy clusters didn't quite match what they expected from the calculations that they made. And they said, hey, you know what? This data really looks consistent with missing matter that is not the ordinary stars that we expect to see. Now, I wasn't around at the time, but I imagine what happened between the 1930s and the 1970s is people said, well, that's kind of interesting. This is a brand new telescope. Telescopes are hard. We don't really understand these instruments, so who knows what's going on? Around the 1970s, Vera Rubin also came to the same conclusion, looking at a completely different scale, looking at spiral galaxies, like the spiral galaxy of the Milky Way that we are in right now. So this is a completely different system. Right? Zwicky was looking at clusters of galaxies. Rubin was looking at spiral galaxies. And the motion of stars within the spiral galaxy also seemed to imply, oh, wait a second, there appears to be missing stuff. Okay. Now, I imagine in the 1970s, if you were a particle physicist, a fundamental physicist, whatever that means, and you just happened to be sitting there in your office, sitting on your thumbs, not knowing what's going on, you had nothing better to do in your life, then you would have dropped everything and thought about this problem. This would be the problem to solve. It just so happens that in this other tribe, and usually the astronomy and the physics floors, there are different floors in the building, so it really feels like a different tribe. In this other tribe, something else was going on. Around this period of time, particle physics, which was a new field, were building new toys, these colliders, where they're smashing together protons and elements and producing all sorts of new and unexpected particles. And it was a puzzle. Why are we getting all of these particles? Where are they coming? Are they inside the atom? What does that mean? And I will arbitrarily pick a period in the 1970s. So my high mark will be the Nobel Prize for what's called the electroweak theory. There was a tremendous effort leading up to this and after this, but this is a benchmark for me for the development theoretically of what we now know as the standard model of particle physics. And it was a heroic effort between experimental and theoretical physics to build this mathematical edifice. And there was one puzzle which had obsessed the community, rightfully so, and that puzzle had to do with the reason why we built the Large Hadron Collider, and that thing is called the Higgs boson. So how many people here have heard of the Higgs boson? I suspected as much. A crowd that comes to Perimeter Institute in the snow outside. So the story then, the apology then, is if we have known about missing matter for almost 100 years, why is it that we're talking about dark matter and the theoretical progress in dark matter in the 2010s, 2020s with fresh new eyes? So, let me continue this biased history. Let's go back to my tribe, particle physics. This edifice that we built up, the standard model, if you ask me, the standard model looks like this. And if you wanted to be fancy and if you visited CERN, you can buy a mug like this, which is roughly the mathematics behind this ugly thing. This ugly thing is a table. And it's a bit strange, but we've seen tables before. Some of us have taken chemistry. Those of us who did poorly in chemistry went on to do physics. But in chemistry, you have the periodic table, right? Anybody here a chemist before I say a few chemists? Now, the periodic table, I'm going to guess not even chemists say, I love the periodic table. The periodic table is so great because I can look up any atomic number and learn the mass and blah, 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 blah. I think that's a fair statement. But the periodic table is fantastic. And it's not fantastic because of the data that is inside it. It is fantastic because the table is an organizing principle. If you have a box on the table, you know there's an atomic number, there's some number of protons, some number of neutrons, da-da-da-da-da. You know if there's something missing. And this is a mathematical picture of what we call the standard model of particle physics. The periodic table is beautiful because as physicists, we understand that the periodic table reflects a deep mathematical organizing principle, and that is quantum mechanics applied to atoms. So this is what third and fourth year physics students do in their quantum mechanics courses. And this thing, this mess of a table, is beautiful, not because there are these weird, funny symbols and they look kind of alien, but because this also reflects an organizing principle. And this organizing principle lives within a generalization of quantum mechanics called quantum field theory. And what this table is, each row is a class of particle, or a quantum field if you want to be fancy. These are their funny names. Each row, 1/2 means these are matter particles. If it's not 1/2, it's a force particle. We'll get to the H in a bit. And each of these columns is one of the 3 fundamental forces of particle physics, so gravity is not included here. And each of these funny symbols is a mathematical description of how those particles interact under these fundamental forces. So if you have new particles, the new particles should have something called spin, which tells you if it's matter or a force particle, and some numbers over here, or some symbols over here. And the one thing that was missing from the standard model of the 1970s was something related to the Higgs boson. It was this question that if we didn't have this last row, something funny happened to our equations when we calculated the likelihood for 2 particles smashed together. And the mathematics were giving us weird numbers like infinity, if that's even a number. Any mathematicians? And the simplest explanation for why this theory would make sense is that there is one more line here, the Higgs boson, that had particular properties, and if you turned the crank, everything made sense. Everything except for one thing. So we had a great idea, find the Higgs boson. If the Higgs boson actually exists, most of you know the answer. If the Higgs boson actually exists, there is one additional puzzle. Why is it so light? We now know that the Higgs boson weighs about 125 times the mass of a proton. if you turn the crank in this theory, you would expect it to be much heavier. So there's this give and take that didn't quite make sense. And so if you zoom back to the 1990s, and you went to the physics floor, the particle physics floor, not the astronomy floor, they had two choices. One choice was this puzzle of why is the Higgs boson light? This was a puzzle that their community had built up to over 40 years of colliding particles and building mathematical models, learning what all these weird symbols and tables meant, and oh yeah, this is an open question. And then there was this puzzle that our friends downstairs, our friends with these funny telescopes, and they go out at night, they're kind of like vampires, and they kept telling us this weird thing about there's missing matter. Okay, which one are you going to work on? Right, the one where there are faculty who will hire you as a postdoc. So this was the most important question. And now I'm going to lead us down to the story of an opinionated, mostly correct story of the weakly interacting massive particle, the WIMP. And this dominated our idea of what dark matter ought to be. And as a scientist, you should be really careful when you say nature ought to be something for about 30 years. And here's how it works. So you have this big problem, this big, deep problem. Why is the Higgs boson light? You do the calculations, it doesn't seem to make sense. But you realize that there's a way to explain why the Higgs boson would be light, and that's to invoke some deep, elegant mathematical principle that would explain why the theory is actually more constrained. Here is one such deep, elegant mathematical principle. It's called supersymmetry. Supersymmetry is some deep, elegant mathematical relation between force particles and matter particles. And they all have silly names. If an electron is a matter particle, there's a silly force particle called a selectron. You have to get your kick somewhere. So what? So this ends up solving this puzzle that we had found. This symmetry, because every particle has a copy, gives you new particles. This theory predicts new particles. All right, so lesson number 1. Mo particles, mo problems. I want us all to be on board with that. So what happened? Oh, this theory has more particles. So what? It turns out the moment you put these new particles in, and you knew exactly what they were, because for every, there's a proton, there's a superproton, all this stuff, protons suddenly have new reactions where they can decay. Well, that seems kind of dangerous. You're here, I'm here, our protons are still around. And in fact, for the physics students in the room, the bound on the lifetime of the proton is actually longer than the age of the universe. So you should think about, how do we have a bound that is longer than the age of space-time itself? But protons are pretty darn stable. So that's not a good feature. But we're thinking, this is some weird practical problem. This elegant, deep mathematical thing was so beautiful. Let's try to save it. And what we do is we put a Band-Aid, a mathematical Band-Aid. And we invent some additional symmetry. There's not deep, not elegant, but we just say, maybe there's some rule that prohibits these interactions. And it has some silly name, R parity. And I will bet you nobody in this entire institute knows what the R means in R parity. I don't know. But what this R parity does, mathematically, you apply R parity, and that means that the interactions that would have caused the protons to decay are no longer allowed. And it looks like everything starts to work again. You solve your deep, elegant problem, and the immediate other problem that comes up seems to be okay, and you start feeling pretty good. You bring your team of graduate students, and you look at this, and you say, hey, what else does this theory do for us? Well, with all of these new particles, and some reason, some conserved, some parity, it turns out the lightest new particle is stable. So the reason why electrons don't decay into neutrinos, which are these other funny particles, is because electrons are the lightest particle that carry electric charge. There's no way to conserve charge if that electron decayed. So the lightest new particle, which carries R charge, is stable, cosmologically stable. And it is at this point that we think, hey, I heard something about cosmologically stable new particle. Oh, it was our friends downstairs. So we go down the stairs and we say, what do you know about dark matter? And the one thing that we knew about dark matter is roughly how much there is. So there's a calculation to be done. And it's a good thing because there's a grad student now in the room who says, hey, you know what you should do? You should do this calculation. And let's be very honest. The first thing the grad student does is, nah, that calculation is hard. And it is hard. It's hard because this calculation is telling you how much dark matter is left over after the Big Bang. So on the one side of the calculation, you're doing this particle physics calculation, something about quantum mechanics and reaction rates for producing dark matter and dark matter annihilating. On the other side of this calculation is something about the expansion of the universe to figure out how much dark matter is left over. So you have gravity, G Newton is in there, and on the other side, you have all these particle physics numbers. And the grad student says, you're telling me that you want me to do this really hard calculation, learn all of this general relativity, and you expect me to match this arbitrary number from these people downstairs who I've never met in my entire 3 years as a grad student? And you say, yeah, it's for your thesis. And wouldn't you know that the number that comes out is the correct number? No, okay, that's a lie. But it was a correct number within a couple of orders of magnitude. Any astronomers, there's at least one astronomer in the front row, but if you're a particle physicist sitting on the 5th floor and the astronomers on the 4th floor, you think, 2 orders of magnitude? That's amazing for astronomy. You're dead on. So we write papers and we celebrate. Okay. You wake up the next morning feeling pretty good about yourself. And then someone knocks on your door. Oh, who's here at 9 a.m.? You open up the door. Professor, that was a fantastic series of paper you wrote about supersymmetry and dark matter. I'm your new grad student. What are we going to work on now? And you think, oh gosh, I don't remember that I hired a grad student. Well, there's one game that I know how to play, and it's this puzzle of why is the Higgs light? Oh, maybe we got it wrong last time. Okay, let's try alternatives. Let's look for some other deep, elegant mathematical explanation for why the Higgs mass should be light. And it turns out one such deep, elegant mathematical solution is to extend space-time, have an extra dimension. Totally weird. Turns out it can kind of work. Well, if you have an extra dimension, what do you get? Like higher modes in the violin string, like higher octaves, these extra dimensions predict new particles. Huh, okay. And what happens when you have new particles? Mo particles, mo problems. Turns out these new particles, when you put them into your theory, screw up all sorts of weird observations that we found over the past 30 years. So that can't be right. It's not quite proton decay, but related to proton decay. And there are weird different flavors of extra dimensions. And so the grad student starts to slump. They say, it's okay. We've done this before. So you invent a humbler new symmetry. It's a Band-Aid, mathematical Band-Aid. It's called Kaluza-Klein parity. What that means is some of these new particles are prohibited from interacting in certain ways, and it ends up curing these observables, just like preventing the proton from decaying. And the grad says, oh, good. What else happens? Well, once you have a new symmetry and some conserved charge, the lightest new particle is stable, cosmologically stable. And the grad student says, okay, and then? Well, what I would like you to do is to read your predecessor's thesis and learn how to do the calculation where this new light particle, this lightest particle with kk charge, how much of it is left over in the universe? And the grad student says, okay, well, I can read the previous student's thesis, but that was like a shot in the dark that it worked out. How do you expect? And you said, just do it. And while the grad student is going through this calculation, you look at this chart and you realize the new particles that you get, you know a lot about these new particles. You know a lot about them because they inherit their properties from the Higgs and all of the Higgs' cousins. Why? Because there is this deep, elegant mathematical symmetry. It's like a mirror. The thing on the other side of the mirror, you know what that person looks like. And so, when the grad student comes back and says, would you believe? You'd say, yeah, it probably works out, doesn't it? And you're starting to realize it's not a coincidence. The details of the calculation change, but the numbers that go in are all basically the same scale numbers. The grad student goes off to celebrate, and you buy a bottle of champagne for their dissertation. Next morning, Professor, oh my gosh, I love the series of papers that you're doing. What's my first project? I'm your brand new grad student. And you think, holy moly, this Large Hadron Collider has better turn on soon because I am running dry. But you think, well, why is the Higgs light? Let's think of a new reason. Maybe there's substructure. Maybe the Higgs is not a fundamental particle, but there are some subprotons and subneutrons that come together to form the Higgs. Oh, okay, so what does that mean? Well, if you have like subprotons and subneutrons and you have other particles, great. Is that okay? No, probably not, because you have all these observables that we have seen, and these new particles screw it all up. Oh, should I be sad? It's okay. We can apply a Band-Aid. This one's called T-parity. I'm pretty sure, actually, people at Perimeter might know what T means, and I should ask. What does it do? Well, it solves this problem, and it means that the lightest new particle is cosmologically stable, and then you tell the grad student, go and do the calculation. I'm pretty sure it's going to work out. Right? It almost has to. The details of this calculation, even though it's on the one side, it's all particle physics, on the other side, it's all general relativity, the fact that they're all the same essential properties, the same essential mass scales, the same essential fundamental couplings, even though the details change, if you're within a couple of orders of magnitude, it's going to land in that window. And it does. And as a discipline, you're feeling pretty darn good. Not only was there this puzzle where you needed a Higgs boson, okay, we predict the Higgs boson, but then you anticipated another problem, and you came up with this deep, elegant mathematical solution, not just one, but three. It's got to be one of these. And each one of those predicts new particles that solves the downstairs people's problems. Not only are we doing great in our field, we're solving astronomy's problems. Good for us. Oh, boy. It's a no-lose scenario. You tell your colleagues, we have to build the collider, we have to look for the Higgs, and then we will learn truth. There's something to see. If you didn't find the Higgs, that's even better. It's a bigger mystery. So, circa 1990s, this is what the standard model of particle physics looked like to a theoretical particle physicist. And this is what experimental particle physicists look like to a theoretical particle physicist, which, of course, I'm joking. This is how progress happens. And the key point is, when you have this no-lose theorem, that there's a deep, meaningful reason to build this collider because whatever comes out, you will learn truth. You very quickly go from this to this. And then even faster than it took to build this, you go from this to this. So how many people here remember the Nobel Prize for the Higgs boson, 2013? Very good. And then remember the Nobel Prize for the discovery of supersymmetry. That's right. The Nobel Prize for the discovery of extra dimensions. Of the compositeness of the, no. So something went tremendously right. There was a Higgs boson, but something went tremendously wrong. So 2013 also happened to be the year that I defended my thesis. It was a thesis. You probably have heard of the chapters. Chapter 1 was supersymmetry, Chapter 2 was extra dimensions, and Chapter 3 was the compositeness of the Higgs, and all of the great new things we would discover at the Large Hadron Collider. I don't know how it happened, but by some happenstance, someone put me in contact with Science News, and the next thing I knew, I was literally the poster child for a particular type of ennui among particle theory graduate students who are graduating right around this time. And it was so great, right? It was a perfect love story, right? You solve this problem in particle physics, and for free, you predict the solution to this other problem. And what this meant was that maybe the love story has a breakup. And like your first love, when it ends, you get a little bit gothy. And that's when I said, you know what, I'm done with the Higgs boson. I am now a dark matter theorist. And there was some reason to this. There's this idea that there is still an open problem and a toolkit for building theories that had not been fully utilized directly for this problem. How do people feel right now, by the way? I know my own emotional feelings about this. It takes some time to get over it. But it's a little bit of a downer. So let's move on to where. And here is where there's a little bit of hope. Right? Because even though this fantastic program of the weakly interacting massive particle, the supersymmetry extra dimensions, composite Higgs, even though all of that didn't quite pan out as well as we had hoped, it worked great for Higgs, we still have the Large Hadron Collider, which probes smaller length scales than ever before probable by the human race. This is humanity's best microscope ever built. We still have labs like Snow Lab, about 400 kilometers north of here, where we have the most pristine environments to look for the chance interactions of dark matter scattering off of a nucleus. Some of the most pristine environments, again, literally ever made by humanity. We still have an upcoming program of telescopes to search for, with higher and higher resolution, for this light from 13 billion years ago. And this is a site in Chile, in the Atacama Desert. And, completely unexpected, we now have gravitational waves, which are literally a brand new way and qualitatively different way of seeing the universe through radiation of space and time itself. We are equipped to make progress on this problem. And so for all that I will apologize, and you know what, maybe the 1990s and 2000s, we were thinking in the wrong direction. This program, some of it serendipitous, is well suited where we have a fighting chance to make deep progress on this question. So for the past 2 years, the North American particle physics community goes through this decadal process where we review what are our priorities, our scientific priorities in our field of fundamental physics. And it should not surprise you that one of the unifying themes was to understand what is dark matter. All right. So that says something about particle physics. That says something about where the field is. I am a theoretical particle physicist. How is it that I search for dark matter? All right, so I have a quiz. This depends on whether or not you're wearing glasses. What is the difference between these two pictures? Anybody? Good. So one of these is the Millennium Falcon. I think this is a screenshot from one of the movies, so let me say this is the Millennium Falcon. The other is a Lego model of the Millennium Falcon. And there's something very deep here that I think it rings true to any physicist. The model is an approximation for the actual thing. If you zoom into the model, if you lift it up, if you look around, if you pick it up, you say, hey, this thing is kind of small to be the Millennium Falcon. But in the right context, you learn something about the Millennium Falcon. You learn, maybe this little deflector dish, which fell off in one of the movies, is roughly the same size as this bit over here. There are things you can learn from a model. But the model is not nature. The fact that you have a mathematical model does not prescribe what ought to happen in nature. And this is where we are. So when you ask, what is it that theoretical physicists do? There's a misconception that we tell you what nature is. We don't do that. We cannot do that. We build mathematical models, and here is the model that we introduced earlier, the standard model, to describe nature and to mock up nature and maybe glean some principles that nature realizes, but that is not a prescription. So there's this great painting. It says, "This is not a pipe." I will spare the Quebecois my attempt at French. But when we do theoretical physics, we are exploring what types of models can explain the dark matter puzzle, and what can we learn from those mathematical models. And like any good crime procedural, there's a motive, means, and opportunity. A mathematical model for dark matter answers these questions. First one is, what is it? Some supersymmetric partner, blah, 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 blah. The next thing is, how did it get here? You have to explain what mechanism created this particle. Then, most of the particles that we know of are actually unstable. You have to explain, why is that particle still around? And given that we've been searching for dark matter for 30 years, then your theory has to say why we haven't found it yet. And any theory worth its weight will tell you, and this is how you will discover this type of particle. It'll give you something falsifiable. And so for the weakly interacting massive particle, there is some deep, elegant mathematical symmetry that explains to you what this new particle is. And that was very deep and exciting and meaningful. Then there's a series of answers. How did it get here? Well, the same way that ordinary particles got here, through something called thermal freeze-out. That was the calculation that we asked the grad student to do over and over and over again. Why is it still here? We have to put that Band-Aid on. Remember, if you put this Band-Aid on, you solve some problems, and for free, you get stable particles. Why isn't it ruled out? Well, for all we know, dark matter might still be a WIMP. How do we discover it? For the WIMP, we keep doing exactly what we are doing because we have the experimental program to probe this. But there are other answers to these questions. Maybe it's less interesting what the deep mathematical principle is before. Maybe we start with, there is dark matter. Let's build the simplest building blocks, the simplest Lego model, the simplest mathematical model, and see what comes out. And then, how do you discover it? You start thinking more creatively, right? If there are different answers to how to get here, you have different interactions, which means there are different reasons why it's stable, and you have different ways in which it will manifest itself. And one of the really great things we've been talking about over the past 3 days here at Perimeter is one puzzle that I'll shout out, which is there are a handful of black holes. So this is a quasar. It's an artist rendition. There's a handful of these. These are galaxies far, far away that are powered by a supermassive black hole. And what's the difference between a black hole and a supermassive black hole? The supermassive black hole is so large that our understanding of how black holes form cannot explain how they got so darn large. And the usual story is that first you form stars, and stars form little black holes combine to form big black holes, but that cannot happen fast enough to explain these gigantic black holes. And one of the really cool things that we've been doing, this is a photo taken earlier today, has been puzzling over the ways in which the dark matter, which we know was already in these galaxies because they held the galaxy together, might be contributing to answering this puzzle. And how this puzzle might be the first step in this refined way of looking at this open question of learning something new about dark matter. All right, so this is just a slice of the type of really exciting types of questions that we've been thinking about. Now I want to change gears here and answer the who. So who gets to do this thing? Who gets the privilege of exploring the cosmos using theoretical physics? And there's an analogy that we often use. Dark matter isn't dark, it's invisible. And the analogy has to do with equity and diversity in physics. Right? And it's probably not surprising that such an analogy would come about. There are a few different analogies. And in the same way that dark matter is a puzzle of missing mass that we don't understand what it is or where it came from, there's this missing talent puzzle. Oftentimes, when you walk into a room in a physics department, the people that you see there have a different demographic makeup than the people that you see outside the university. And the analogy here is, why is it that we've discovered all this stuff about atoms? Like, we know all sorts about chemistry, we know about biology. It's because ordinary matter, protons, electrons, neutrons, neutrinos, well, not neutrinos, are charged under electromagnetism. That is the probe that we use to see, smell, taste, hear everything about matter. Dark matter does not seem to have that privilege of being charged. That means our telescopes, our microscopes, all our tools do not automatically work the way that they do for ordinary matter. That doesn't mean that dark matter doesn't exist. That does not mean that the talent doesn't exist. And there's a lot of fantastic books writing about what this is. These are people who are far ahead of their journey in thinking about this puzzle than I am, and I encourage you to take a look if you're interested. But another way in which this is analogous to the puzzle of dark matter is that this is not a puzzle of missing data. Just like Katie's slide, we have many, many reasons to believe that there is a missing mass problem. And there's no shortage of data that across different types of demographic slices, whether it's gender or ethnicity or unseen things like socioeconomic background, belief, political background, all of these things, the demographic inside the ivory tower is different from the demographic outside. So it's not a matter of missing data or orders of magnitude in astronomical observations. Like the puzzle of dark matter, maybe the way that we have been doing things might not be the best way. Maybe there should be new approaches and new theoretical constructions, new frameworks to approach this puzzle. And when we think about this, there's something that oftentimes well-meaning people will say in earnestness. Well, but physics doesn't care about the color of your skin or your race or your gender. Maxwell's equations are indifferent to the human who is creating them, right? It's a reasonable thing to say. But oftentimes, the people who say this at one stage of their career go on, and then there's inevitably some road bump, because we all hit road bumps, and then there are different things that are said. Oh, well, the committee would have selected me if only I had this fancier university on my diploma, if only I had this fancier knick-knack on my CV, or if only I had advanced calculus when I was in high school, I'd be able to do research when I was in my first year of college. Or when one's hand is the only brown hand in the classroom, maybe it's a little bit harder to be the one to ask a question. And I mention these because these are sociological human issues, even though the subject itself is indifferent to the humanity. And to be able to do this is a human endeavor. I argue, though, this is still the wrong way of thinking about it. So how many people here saw Oppenheimer? That's a smaller percentage than I expected. So one of the characters in Oppenheimer is Vannevar Bush. This is his character over here. And for those of you who saw the movie, the person he's shaking hands with is the villain. But Vannevar Bush was the architect of what is now known as the National Science Foundation. And this is the report written during wartime where Vannevar Bush advocated for the US to form a funding body to support not applied research, not military research, but research in fundamental science. I will say that the National Science Foundation and its cousin in Canada, NSERC, have been perhaps the greatest forces in fundamental science in the history of mankind. And I do not mean that ironically, this is true. Right? The commitment to fundamental research that these institutions have put forward. I would say that even if I were not currently funded by the National Science Foundation, but I feel like I should mention that. But this is true. And this report is online. If you look into this report, there is this phrase by a chemist, James Conant, in every section of the entire area of the word, every section where the word science may be applied, the limiting factor is human. The limiting factor is human. And so here's the version from Perimeter Institute, Rob Myers, the director of Perimeter Institute. We can't afford to leave any great thinkers or any great ideas behind. The limiting factor is human. So you might have the best microscope humanity's ever built. You might have the most pristine environments to look for dark matter scattering off a nuclei. You might have the ability to see with finer resolution than ever before the first light of the universe, and you might have a damn new way of seeing the universe itself. But the thing that is holding us back is human. This is the value of places like Perimeter. This is where the progress is. And if you ask purely about scientific interest, you're saying nothing about fairness or equity or any of these things. When you want to draw people to this calling, you want the people who will sacrifice and work hard and who are willing to do this. This is a hard job and it's difficult work, tough problems. You want to be able to draw from not just the 15%. You want that entire 100%. Right? The power of full participation is analogous to the Standard Model. The Standard Model does a lot of great things. Chemistry is because of the Standard Model of particle physics. But dark matter creates galaxies. So let's do one last question. That's how we do it, who does it, who gets to do it, why do we do this? And whenever I think about this, there's a painting by Paul Gauguin. Who are we? Where do we come from? Where are we going? In some order. And I think about this. Why do we do science? I think about this painting because it reminds me that every culture, for as long as humanity has been human, has had a story, has had a cosmology of how we belong, how we came to be who we are, where we came from. Right now, science is part of our cosmology as a global human species. And we have our own story. And that story is something like this. 13 billion years ago-ish, there was something called the Big Bang. We don't quite understand what happened. It's curious. The Big Bang formed a lot of the matter and stuff in our universe. A good chunk of that stuff is dark matter, which you see here in these weird filaments. The universe expanded rapidly and cooled down, and these filaments condensed. Where these filaments overlapped, there was an overdensity of gravity. It started pulling in more dark matter. That dark matter overdensity then had a bigger gravitational pull and started pulling in this really funny stuff called hydrogen gas. And that hydrogen gas collected into this clump of dark matter, and eventually the hydrogen gas found each other, and they started forming these funny things called stars. Some of those stars would go supernova and produce metals, and you would form more complex stars. Those would get together into things called galaxies. In the galaxies, you'd find these little solar systems, and the next thing you know, there's a planet called Earth, and there are these people who are little goldfish who are just discovering the dark matter ocean that we happen to be living in. And that is why we do this. So thank you very much.
Thank you so much. All right, so we have time for questions. So as I said before, there's a microphone there on the stairs. So if you have a question, please make your way to the microphone if you can.
I'm more from a philosophy background, and they don't always like our questions. Have you heard of Klein's 2 dogmas of empiricism?
No, I'm not familiar with. Sorry, and should you stand up for the microphone?
Klein's thesis is called the undetermination of theory by experiment.
Ah, okay.
Do you want me to explain it?
Please.
So Dehaene had a great influence on Einstein and Mach. He wrote a book on the nature of physics in 1908, I believe. And what he was claiming that every theory involves theses that can never be reduced together. So it kind of confirms what you're saying. So let's say a theory how a telescope works is part of your structure, but the theory of light of how that new telescope works, is part of the theory. So you can never go to groundwork. He actually criticized Karl Popper, who thought that everything had to be verifiable. And he said, no, you can never do that. And he thought even basic ideas of physics like motion and stuff like that, we always have to have a point of reference. But everything in the universe is moving, so how do you have a point of reference for all the motions of the universe? So that's the basic thesis. So that's called the Dehaene-Quine thesis, and it's one of the most important things in 20th century philosophy and it's called Two Dogmas of Empiricism. What Quine was saying about the dogmas of empiricism is that we have a way Kant had the idea of the way we think of the world and the way the world is, and he created this idea of the thing of itself. And Quine attacks that idea and says it's a false idea because how we perceive things is then changed. So the theory, we don't work that way, and the things get actually mixed together. So that's the basis thesis. So you might want to look it up. It's called Two Dogmas of Empiricists by Willard Van Hoop. And it confirms exactly what you're saying in a certain way. So, okay, thanks.
So yeah, I can offer, I'm afraid of saying this in the wrong way. My best friend at UC Riverside is a philosopher. and I think I'll say one short thing on that, which I thank you very much for sharing that. Part of what I wanted to share here was the way in which my sub-tribe of particle theory thinks about theories. And what you're saying is exactly, it is a philosophical question. But thinking about capital T theory, where this is some framework for everything. And I think what's relevant here, epistemologically, is that the theories that I'm talking about here are lowercase t theories. And that's why I emphasize by the Lego analogy that these are toys that are meant to do one thing.
That's exactly what the Ham says and Quine says as well. And actually, there's a philosopher at U of T called Bas van Frazen, and he says that as well. So all three independently agree on that.
Thank you for that. Yeah, all right, so we have some questions from the online audience. And if you have questions in the audience, please feel free to make your way to the microphone. Let's see. We have plenty of questions from online. So here's a good one. If we found dark matter, what other physics mysteries would be easier to solve with that new information?
Ooh, that is a really good question. Thank you, person in the universe who asked this. We have a list of puzzles, and depending on what it is that we find, how we find it, there are different ways of piecing that into these puzzles. And so one way of playing this game that we play as particle theorists is pick your favorite particle physics problem. Why is there more antimatter than matter? Or sorry, why is there more matter than antimatter in the universe? Why is it that certain particles have these weird properties? Why is it that the Higgs boson is light? Right? That problem is still out there. And then you play this game of, there's this new telescope coming online. If that telescope has this new ability to see the world in a certain way, what implications does my proposed model, my toy theory, imply for that telescope? And so there's this whole, in fact, in our conference, we had this fantastic figure where it was a flow chart of, if you see this, then what do you think it could be, and what is the next experiment that you do to verify that? But the question hits exactly at the heart of what it is that we're doing.
That's great. Go ahead.
Can you comment on the modified gravity theory introduced by John Moffat that claims to explain cosmological data without dark matter?
This is a fantastic question. Thank you. So modified gravity, or Cousins' modified Newtonian dynamics, this is an alternative to what I was saying where let's all get on the same page and dark matter is a new particle. Thank you very much for pointing this out. And so this is a different proposal. People have different opinions about the viability of these proposals, embedding it into a full theory, a capital T theory. But that's all human opinion, right? We call it Bayesian priors, about what a good theory ought to look like. What's really neat about modified gravity is that it is a proposal that has value in the space of understanding what dark matter is. And I'll give you an example of this. So even in my tribe, there's this idea called self-interacting dark matter. You know, dark matter isn't just inert, sometimes it bounces off of itself. And what modified Newtonian dynamics tells you is that maybe gravity behaves a little bit differently on different scales. One of my colleagues at UC Riverside, Haibo Yu, realized that, that theory has some merit in connecting to experiments. That's really exciting. I have my own pet theory, if that dark matter will bounce off of itself. And if dark matter bounces off of itself, the distribution of dark matter in these bubbles, in these halos, would be different. It'd be more puffy. It's like a popcorn machine. And if dark matter is more puffy, that means the gravitational interaction, the net gravitational interaction, will be a little bit different. And if it's different in just the right way, it can end up looking like modified Newtonian dynamics. And say whichever tribe you follow and whatever you prefer as a human being, experiments will figure things out ultimately. But the fact that there's this idea led to cross-pollination of new ideas and new observables, and this is the key point. What happened was the community was able to say, we should look for this type of observables in our new telescopes, and that will teach us something. And so I know a lot of the way people frame this is as a debate between one camp versus another camp. We're all on the same team trying to discover truth here, and I think that's a really fantastic example of that.
Hi, thanks a lot.
Hello, thank you.
Pretty simplistic question, I think. My background on this is so elementary, so please forgive the silliness of the question if it comes off that way.
You start the question, now I'm terrified.
No. The idea that dark matter, the candidate for dark matter that you're discussing is a massive particle. The fact that there's like 85%, et cetera, like instead of it being a few massive particles, what about a whole lot of really light particles? And is that still in the running? Very good.
That is not a simple question. That is a deep and insightful question. And that's a question that we ask ourselves over and over again. Good. The mass range for plausible dark matter candidates, which again, plausible is something that human beings make up, is actually incredibly wide. On the one end, you could have gigantic 10 to the 30 solar mass black holes. On the other end, you can have things which one would barely call a particle, quantum mechanically. What I will offer here, instead of just saying, it could be anything, what I will offer here is, okay, what do we know about dark matter? The puzzle exists. We also know roughly how much there is. And there's one other thing that I hadn't yet told you. We also know, in fact, the way to say this, dark matter is cool. And not just in the hip way, but it's cool in that it is cold. It's non-relativistic. Today, dark matter isn't traveling very fast. And we know that because it had to form these bubbles, these halos, that were needed to collect the hydrogen to form stars, to form everything. So the limits on can dark matter be a bunch of light things rather than a few heavy things is actually set by if they're very light, are they also moving very fast? And if they're moving too fast, you can't do it. So it's a very deep question, and you actually had the exactly right intuition that you can have a bunch of heavy things, or sorry, a bunch of light things, which would be equivalent gravitationally to a few heavy things. So yeah, thank you.
All right. Thank you so much to all of the folks who asked questions. Thank you to our online audience, and thank you so much to Professor Tanedo.
Thank you.